From today, we are going to start a new lecture series in Chemical Reaction Engineering 1. We will discuss what we are going to study in this paper 1. Mainly, we'll be dealing with homogeneous kinetics and reactor design. We'll consider ideal reactor models, batch reactor model, mixed flow reactor model, plug flow reactor model, and interpretation of batch reactor data. We'll be studying the kinetics of elementary as well as non-elementary reactions, kinetics of zero order, first order, second order with different stoichiometry. Then we'll be studying reversible reactions, reactions in series, reactions in parallel, series parallel combinations, special categories of reactions such as autocatalytic reactions, reactions of shifting order, and so on. And then we will see the performance of batch reactor, mixed flow reactor, and plug flow reactor with various rate laws defining different kind of kinetics which will be studying. Then we will also study the different reactor schemes, reactors in parallel, reactors in series, different combinations, plug flow, mixed flow combinations of same size, of different size, and so on. So different reactor configurations. We'll also study the recycle reactor. Then we'll study temperature and pressure effects. And finally, we will see the introduction to non-ideal reactors. So today we'll begin with our first topic, and we'll start with chapter number 3 of Octave Levenspiel, and we'll be studying different reactions, kinetics of different reactions. The title of the chapter is Interpretation of Batch Reactor Data. So we'll start with batch reactor concept, constant volume batch reactor system, definition of fractional conversion and equilibrium conversion, then design equations for zero order, first order, second order, irreversible as well as reversible reactions. Then we'll see the graphical interpretation of these equations and their limitations. Then we'll extend our discussion to variable volume batch reactors, and we'll study design equations for first order, second order, reversible as well as irreversible reactions to be conducted in variable volume batch reactors. Then we'll study the multiple reactions stoichiometry, rate equations for series and parallel reactions, chain reactions, development of rate expressions, and the problems from the exercise of chapter number 3 from Octave Levenspiel. So first, let us discuss a typical chemical process. What we want to do in a chemical reactor. So every industrial chemical process is designed to produce economically a desired product from a variety of starting materials, which we call as raw materials, through a succession of treatment steps. Now these steps involve physical treatment steps as well as chemical treatment steps. So we feed the raw material before we take it to the reactor where the chemical step will take place. Some physical treatment is required, so physical treatment steps. Then it comes to a reactor, and we have here chemical reaction mainly. And after the reaction is completed, we get the products. Number of products we may get. some unreacted material may be there. Then we have to separate. Suppose we have products C, D, and C is desired product, D is undesired products. So we have to separate out these, and for that different physical steps may be required. So separation processes, different separation processes which we have studied, and finally you get your product from the raw material. So in between you have these things. Then as I said, there may be some unreacted reactant. So that is also separated, and that can be again recycled to the reactor, or sometimes you need to take some physical steps. That also is possible, but most of the times it is directly taken to the reactor. Then we have to answer two important questions. One of them is how far the reaction will proceed, and that is decided or answered by thermodynamics. You know delta G is equal to minus RT ln Kc, and this Kc is nothing but equilibrium constant, which is nothing but the ratio of forward rate constant and reverse rate constant. So this will decide, thermodynamics will decide how far the reaction will proceed. Will it go to completion or not? If it goes to completion, means conversion is 100%, then it is irreversible reaction. But you will find that most of the reactions are reversible, almost all, and equilibrium conversion will decide how far the reaction will proceed. If equilibrium conversion is 50%, then you will get maximum possible conversion is 50% only. So how far the reaction will proceed, or you can say the extent of reaction, is decided by thermodynamics, by delta G, Gibbs free energy. Then second question is how fast the reaction will proceed, and this is answered by chemical kinetics. So minus Ra is equal to K Ca raised to N. So this equation is known as rate equation or rate law. And if we know the kinetics or the rate law, equation of nth order, this Ca raised to N, this index to the concentration, Ca is concentration of A. This N is the order of the reaction, and this K is the rate constant. Minus Ra, minus sign is because it is disappearing. A, reactant A is consumed. So rate of disappearance of A or rate of consumption of A is defined as equal to K into Ca raised to N, where N is the order of the reaction. If we know the kinetics, so this equation known as kinetic equation or rate equation or the rate law. So that means if we know the rate law, and in that we know the rate constant. So depending on the value of the rate constant, so rate constant value will tell us how fast the reaction will proceed. So reaction can be extremely fast or instantaneous. That means as soon as the reactants come into contact, reaction will be complete. Then it can be very fast. Maybe it takes time of 1 to 10 seconds only. Then it can be a fast reaction, completed maybe within a minute. Then moderate reactions. So you can say 1 minute to 30 minutes, 2 minutes to 30 minutes, and so on. Then you have slow reactions, that you can say roughly 1 hour to 4 hours, 5 hours, 6 hours. Then very slow reaction, maybe around 24 hours, 36 hours, and extremely slow reaction. This can take place in days and in months also possible, and years also. Very slow reactions. So we'll see uh, these kind of reactions, and what is important immediately to understand is two things. The extent of reaction means how far the reaction will proceed. This question is answered by the thermodynamics. You should know delta G. Delta G is equal to minus RT ln Kc. Once you know Kc, equilibrium constant, you can find out the equilibrium conversion. Second question is how fast the reaction will proceed. If you know the rate law, that means if you have the knowledge of rate constant, the numerical value of rate constant, then you can tell whether the reaction is instantaneous, very fast, moderate, slow, very slow, or extremely slow. Ultimately, we are interested in reactor design. So for reactor design, you require the information, knowledge, and experience of these subjects. Thermodynamics, you must know. Chemical kinetics, yes, that we will be studying now. Thermodynamics, you have already studied. Fluid mechanics, you have already studied. Heat transfer, you have already studied. Mass transfer, you have already studied. Economics, maybe you will be studying little later. Economics is also important. And when we want to study the reactor design, or finally to be able to design a reactor for a particular reaction, we should have the knowledge of chemical engineering, thermodynamics, chemical kinetics, fluid mechanics, heat transfer, mass transfer, and finally economics. So we'll see these things while we'll be studying reactor design. So here this is a typical reactor where, let us say, reactant 1 and reactant 2 are entering. So this is entry of the reactor. So input is reactant 1 and reactant 2. So these are, say, raw material after some pre-treatment or some physical treatment. Raw materials are ready to be taken into the reactor. Then these are control valves, electronic control valves that will control the flow rates of these reactants. So this is floor level. Above the floor level, you have this section. Here, vent system is, pressure is built up, high pressure is built up, then you can release it from this vent system. Then you have a stirrer, motor driven stirrer. Below this floor level, you have major part of the reactor here. So its volume is huge. If you have seen industrial reactor, you will see there will be floors, maybe below this floor level, this section is there. Here you have arrangement of coolant. So not only coolant, sometimes heating is required. So either it will be heating fluid, thermic fluid, or coolant. In case of exothermic reactions, we will have to continuously take out the heat to maintain the isothermal temperature. So this is an example of external heat exchanger, you can say jacket type, and coolant is entering here and leaving here. And this is the overflow. The level is maintained here. Here you have a level gauge, and the level is controlled by manipulating these flow rates with the help of control valves. Once the steady state is reached, mostly the level will be maintained. So this is output. So this represents input where you have you are supplying reactant 1 and 2, and here is a product outlet, so output. Here two things are important in the analysis of any reactor: contacting pattern and kinetics. Contacting pattern is nothing but how materials flow through and contact each other in the reactor. How early or late they mix. So early mixing and late mixing. These concepts we'll see when we'll study introduction to non-ideal reactor design. Their clumpiness or the state of aggregation, which is nothing but coming together. By their very nature, some materials are very clumpy, for instance, solid and non-coalescing liquid droplets. So some materials may be very clumpy, means they will have the tendency to aggregate, tendency to come together. Then second important thing we must consider is kinetics. That means how fast things happens or how fast the reaction takes place. If reaction is very fast, then equilibrium tells us what will leave the reactor. Because if it is very fast, we will not be able to take out the periodic sample for determining the rate law, and we have to depend on equilibrium. We will see these things in details later. If not so fast, if the reaction is not so fast, then the rate of chemical reaction and maybe the heat and mass transfer too will determine what will happen. So not only the rate of chemical reactions, but rate of heat transfer and rate of mass transfer will also come into the picture. So these things we will see in details later on. Now here you can see the classification of chemical reactions useful in reactor design. So we can classify it as non-catalytic reactions and catalytic reactions, and homogeneous and heterogeneous reactions. Homogeneous reactions we'll be studying in this semester. So in non-catalytic, most of the gas phase reactions and fast reactions such as burning of flame, etc. Catalytic, most of the liquid phase reactions where we use liquid as a catalyst. Example is acid catalyzed reactions and so on. Reactions in colloidal systems, enzyme or microbial reaction. So where we use an enzyme which we also call as culture, which acts as a catalyst. Then heterogeneous reactions: burning of coal, roasting of ores, attack of solids by acids, gas liquid absorption with reaction, reduction of iron ore to iron and steel. These are non-catalytic, mostly gas solid as well as gas liquid reactions. Then catalytic reactions: ammonia synthesis, oxidation of ammonia to produce nitric acid, cracking of crude oil, oxidation of SO2 to SO3 and so on. Now these heterogeneous systems you will be studying in chemical reaction engineering 2 in the next semester, and now we'll focus on homogeneous reactions only, catalytic as well as non-catalytic, in this semester in chemical reaction engineering 1. Heterogeneous systems are all these things. The video lectures are already available on YouTube. Chemical reaction engineering 2, 31 lectures are available on YouTube. Those who are interested can have a look at those lectures also. So from today I am starting this lecture series for chemical reaction engineering 1, and most of the topics will be covered in next 1 or 2 months. So cutting across this classification is the catalytic reaction whose rate is altered by the materials that are neither reactants nor products. So you know catalyst is neither a reactant or nor a product. It doesn't take part in reaction, but it helps to improve the rate of reaction, to enhance the rate of reaction. So we will also see the fundamentals of catalysis and discuss how it happens, that in little bit more details. These foreign materials, so they are neither reactants nor products, but we use it, we call it a foreign material, and these are nothing but catalysts, and these need not be present in large amount. A small amount of catalyst serve the purpose. So catalysis also we'll study in little bit details, fundamentals of catalysis. Now coming to the most important starting point, rate of reaction. How we define the rate of reaction? We define the rate of reaction Ri. When I use plus sign, that means it is for formation. When I use minus sign, it is for disappearance or consumption. So Ri is nothing but moles of I formed. I is some species. So reactants can be, we can call reactant A, B, C, D, whatever. So I, any species I, moles of I formed per unit volume of fluid per unit time. So here V, capital V is volume of fluid, means not the volume of the reactor but the volume of the reaction mass. You can see here, this volume of the reactor means this much volume, almost. Let us say it is 1000 liters, and you can see roughly it is almost 80% filled. So if it is 1000 liters, so 80% means 800 liters. So in this case, capital V, volume of reaction mass. So in our definition, V is always volume of reaction mass or volume of the fluid. So moles of I formed per unit volume of fluid per unit time. So moles formed per unit time. Ni, N is number of moles of I. So dNi by dt is number of moles formed per unit time, and this is 1 by V is per unit volume. So our definition of rate of reaction is, if it is rate of formation, is 1 by V dNi by dt. If we want to write in terms of rate of disappearance, and that's how we'll write most of the times, as rate of disappearance of some species, so we'll use minus sign. So we'll be studying from this book by Levenspiel, and this mostly deals with finding the expression to relate input to output of various kinetics and various contacting patterns. So we'll be studying various kinetics and various contacting patterns, and we'll find these expressions defining the rate of reaction. So output will be a function of input. Then we have to consider kinetics and contacting pattern, and such relationship is known as performance equation, the performance equation. And why this performance equation is important? Because this expression, using this expression, we can compare different designs and conditions. We can compare different designs and conditions, and finally find which is the best, and then scale up it for larger units or commercial units. So the performance equation, it is also called as design equation, is very important for us, and it is nothing but a expression relating input to the output for different kinetics and contacting patterns. So kinetics is defined by this, the rate law, minus Ra is equal to Kca raised to n. Minus Ra is nothing but minus 1 upon V dni by dt. And further we write these in terms of concentration of A. So concentration time data we need for interpretation of a batch reactor. But to find out a performance equation or design equation, we need to relate input to the output and with the knowledge of kinetics and contacting patterns. So here for homogeneous cases we will be studying batch reactor, where uniform composition is there everywhere in the reactor, but the composition changes with respect to time. So here types of ideal reactors. So we'll be studying ideal reactors and ideal reactor design first. So batch reactor. So what we do here, we charge the reactant at once and wait for reaction to go for completion or up to its equilibrium conversion, and then take out all this reaction mass which is now converted into products, and again we make this reactor ready after cleaning and all that for the next batch. So operation is batch wise. So charge at once, take out at once, clean it and charge another batch, and so on. So when the batch is charged until it is taken out, let us say a batch time is of 10 hours. So if you take the samples maybe every 10 minutes or 15 minutes and analyze it, you will find that the composition is changing with respect to time. Next is plug flow reactor and mixed flow reactor. So this is batch reactor, and plug flow reactor and mixed flow reactor, or CFSTR, constant flow stirred tank reactors. These are continuous reactors. In plug flow reactor, fluid passes through the reactor with no mixing of earlier or later entering fluid and with no overtaking. So this flows as a plug. You can see it will travel through this length slowly, and there is no overtaking or no mixing. So at any section here you will have progressive conversion. So here conversion is 0, here conversion may 5%, 10% and so on at steady state when input is equal to output. So at steady state there will be some pattern here. So along the length the conversion is progressive. So if you take out the samples along the length, you will find different conversion. So this we will study in details in the reactor model. Then you have mixed flow reactor or constant flow stirred tank reactor, CFSTR. We will call this as mixed flow reactor, MFR, and plug flow reactor, PFR. So most of the times I will be referring to plug flow reactor as PFR and mixed flow reactor as MFR, and mixed flow reactor is nothing but constant flow stirred tank reactor. So in mixed flow reactor there is uniform mixing. So here you have input raw materials, output, and continuous. This is continuous. Okay. So in batch reactor we will charge at once. This we will stop and wait for reaction to complete, and then you take out these things at once. In continuous reactors, so here this reaction, this reactor which we have seen here, the level is maintained, and if you continuously maintain your input of raw materials and continuously withdraw the product maintaining this level at steady state, this will act, or this will be your mixed flow reactor. And the textbooks will be using in this course are Chemical Reaction Engineering by Octave Levenspiel, and for few topics or maybe few problems we may also refer from Elements of Chemical Reaction Engineering by Scott Fogler.